Okay, instead of talking about ultimate goal, I think so let us talk about steel material preparation, because ultimate goal for a person is the ultimate bliss, to attain the ultimate bliss. You understand what you mean? What does it mean by that? That means from where you have come, you end up there. Where from you have come? Any idea? Then it goes to that fundamental question, where from the universe, right? Well, there are a lot of theories, but my theory is, if you take 0 in the middle, you go right, where do you end? Say plus infinity. You go left, where do you end? Minus infinity. So basically plus and minus infinity, probably they are meeting at one point. To maintain equilibrium, positive charge and negative charge should balance. So if I assume that to be some kind of charge, so it should balance. That means they should be together at a neutral state. So that can be the starting point, or 0 can be the starting point. Probably 0 is the starting point. So wherever you go, you end up again at the same place. That means from 1, everything has formed, again it will end at that 1, right. So that's the ultimate goal, but temporary interim ultimate goal is to get a good job. That will take some million years to reach to that point, right. But interim goal is to get a good job, get a good placement, good salary, good status. So that is available. Now you can bargain for that, but for that you will have to have a well, some interest in the subject. That's how. Okay. Anyway, so let us till now we had been talking about various things. Well, till now we had been talking about the structural items, right? Now let us come to the sort of to the material with which these are made, built. So that is steel. Though in shipbuilding, I mean, there are various types of materials are used, right. As far as the main hull construction is concerned, as well as the superstructure, it can be steel, it can be composite, fiberglass composite, it can be aluminum, it can be titanium, right. Certain things can be stainless steel, I mean, different variety of steel, right. Even it can be wood, for that matter of fact. In some places, people have used ferro cement. So there are various materials can be used for various applications. For the time being, we will concentrate only on steel, right, on steel. Now, steel again is a very vague word, because there are 100 and 1000 types of steels. The steels which we generally use is low carbon manganese steel, low carbon manganese steel, right, kind of alloy steel where the carbon content and the alloying elements are kept at a lower level, such that some parameter called carbon equivalent, which remains below 0.4. We try to keep the carbon equivalent. There is some parameter which is referred to as carbon equivalent, try to keep it less than equal to 0.4, because if you can achieve that, it has been found out that steels having carbon equivalent less than 0.4 gives you better weldability. You can weld it easily. If it is greater than 0.4, then welding is difficult. Difficult means it's not question of difficult to melt it or fuse it, but you weld it, it cracks for some other reasons. Anyway, so we talk about primary steels, which are low carbon manganese steels. Well, putting different alloying elements, subjecting it to different heat treatments, we can get higher mechanical properties. We can get those higher tensile steels, still keeping the carbon equivalent low. So we get steels called HSLA, high strength low alloy, high strength low alloy steels. So one way of telling is that normal strength steel right, and another is high tensile steel. Normal strength steel means steels whose yield stress is of the order of around 220 to 240 what unit? Well, megapascal, yes, or newtons per millimeter square, right, newtons per millimeter square. I somehow feel more comfortable with this unit than megapascal or all. Anyway, and high tensile steel is where the yield strength is greater than greater than equal to around 320 newtons per millimeter square, right. So, any steel having yield point stress above 320 and above are referred to as higher tensile steels, right. They are also at times referred to as high yielding steels, which are in short they are written as HY steels, high yielding steels. And also we have talked about HSLA steel. So, what is the difference between these two? Both these are high tensile steels. Though in shipbuilding, in offshore platform building construction, I believe around 80 to 85% of the steels used will be normal strength steel. In some specific cases, specific requirement will go for higher tensile steels, for the simple reason that higher tensile steels only will use where we have a so called what do you call weight restriction. This what's the use of using higher tensile steel? Why do you use? Reason is it can sustain higher level of stress, or in other words, I can keep the scantlings down, the thickness of the plate, the dimension of the sections, I can keep it low for the same given load. If I use a normal strength steel for the same given load, the plate thickness, if it works out to be 16 millimeter, using a sufficiently high strength steel, that thickness may come down to 12 millimeter. So, I have a weight saving. So, wherever there is a restriction in weight, like if you want to have higher speed, you need to bring down the weight of a vessel. So, in such cases, specific requirement of reducing the weight, then only go for higher tensile steel, otherwise not, because otherwise if there is no weight restriction, I use normal strength steel, the weight will be heavier, okay, let it be, right. If it does not affect my functionality, if it does not affect my cargo carrying capacity, so it's better to use normal strength, for the simple reason they are cheaper. First reason is they are cheaper than high tensile steels. Second reason is they are less prone to fatigue failure. That is one important aspect. Normal strength steels are less prone to fatigue failure. Fatigue failure is nothing but a kind of failure which is initiated through a crack formation. A crack is formed and eventually leads to a catastrophic failure. So, that is less probable in case of normal strength steel. Anyway, but still, for example, submarine, you will rather go for a higher tensile steel because of the kind of loading they are being used. I mean, kind of load it is being subjected to. It is subjected to a what do you call hydrostatic pressure, severe hydrostatic pressure. Whereas a ship, a floating ship, a displacement craft, if I use high tensile steel, I use very high tensile steel, what would be the result? Result will be that weight will be less, definitely, and section dimensions will be less. So, it may result in lower stiffness. it may result in lower stiffness and lead to a deformation of the entire vessel. The whole vessel may get deformed, may get bent under its own weight, because the stiffness is less. It's something like, equivalent analogy would be, you take say 1 meter long bar, 2 bars you take, one having with a material having high modulus, another having less modulus, or one having high stiffness, another less stiffness. If I hold like this, the one having less stiffness will sag. Which one will sag? The one who is having lesser modulus of elasticity, leading to lesser stiffness of the material. So, it will sag under its own weight, another will remain straight. So, that could be a problem, right. So, if that is a problem, then you will have to put sufficient stiffening material to make it stiff, such that it does not deflect beyond permissible limits. So, what it will result into, the whatever weight savings you had because of higher tensile steel, that is lost. That is why, in fact, for cargo carrying vessels, merchant vessels, we do not go for higher tensile steels. It is all normal strength steels. Whereas, in case of submarine, it is subjected to hydrostatic pressure, load. So, their question of that stiffness or deflection is not there. It is a different kind of load is coming, it is not a bending load. So, a high tensile steel is a good proposition. Anyway, we are talking a little bit about material before we go for steel material preparation. So, here we see that normal strength steel and then the high tensile steel, it again has high yielding steels as well as HSLA steels. They are nothing but both are having similar kind of strength, but high yielding steels generally have carbon equivalent greater than 0.4, right, whereas HSLA steels will have carbon equivalents less than 0.4. That is the main difference. Physically, with mechanical properties, both are somewhat similar, right. You have HY, generally these steels are designated in this fashion, say HY80 or HSLA80. This is nothing but high yielding steel, yield stress is 800 newtons per millimeter square. High strength low alloy steel, yield point is 800. Imagine, our normal strength steel is hardly 240, this is 800, substantially strong. There are HSL 100, means 1000 newtons per millimeter square, very strong steels. Anyway, so the difference between HY80 and HSLA80, fundamental difference is that for this carbon equivalent will be much more than 0.4, here carbon equivalent will be still less than 0.4. So, high yielding steels are difficult to weld by conventional welding methods, right. They are difficult to weld with conventional welding methods, because you do it through a conventional welding method which is used for normal strength steel. This will again crack. You will weld it after the weld has cooled down, or during its cooling down it will crack. That means you cannot weld. So, that is why it says that if carbon equivalent is more than 0.4, the steel is not weldable. That is how it is said. It is not weldable, or weldability is poor. That is how later years this HSLA was developed, which gives you the same mechanical properties as those of HY steels, but improves the fabrication quality. That means the carbon equivalent with the method it was made, that the alloying content were kept low, thereby carbon equivalent is less. Carbon equivalent means carbon and other alloying elements equivalent to carbon. That is how this term. So, HSL steel carbon equivalent is low and it is easily weldable. That means you can weld it with the conventional technique as you implement in case of normal strength steels, right. So, that is about HSL steel. Obviously, all these are at a cost. HSL steel is very expensive, because you have all the benefits. You have the strength as well as you have weldability, low carbon equivalent, right. So, it is more expensive than HY steels, but for construction point of view, naturally preferred would be HSLA wherever you use higher tensile steels. Anyway, whether it is a normal strength steel or higher tensile steel or high yielding steel or HSLA steel, all steels as it comes to the shipbuilding yard, we get it in form of plates, rolled plates, right. Those rolled steel plates, they come with a coating on top of the steel plate. That coating forms in the process of manufacturing the plates. That coating is referred to as mill scale. This is essentially, it is nothing but you have the, say, the steel plate over which, as if there is a layer, it is covered with a thin layer on both the sides, which is referred to as mill scale. So, as you can see, the name mill scale means that some scale has formed in the rolling mill. How these steels are formed? They are essentially rolled, hot rolled from bigger ingots. That means, suppose you are making HSLA 40 steels. So, basically what you will do? You will produce composition of HSLA 40, means whatever alloying elements are needed or normal strengths, whatever, and you take it out in the form of ingot from the so called steel plant. After all that process of alloying, etc., deoxidation and whatever manufacturing process of steel, you get the ingots. Ingots will have a rather of a squarish shape, right, and that will be then passed subsequently through a series of rollers, such that you end up at the last rolling mill where you have the required thickness. So, from a huge thick ingot, you bring it down to thin plates. Thin means it can be 4, 5, 10, 15, 80, 40 millimeter, whatever thicknesses, different thickness you roll it out. So, the entire process is hot rolling. Hot rolling means when the ingot is hot at a temperature of around 800 plus degree centigrade, it is red hot, right. So, what happens then? At that temperature, you are putting it to substantial pressure and rolling it out. So, schematically it may look something like this. So, the ingot is under tremendous pressure, the rollers are rolling and it is squeezed out as if. So, there will be set of such rollers till you get the final thickness, and this is being done at elevated temperature. So, what happens to the surface? Apart from the whole thing is getting squeezed, getting thinned out, right, because steel is a malleable material. Had it been a brittle material, this would not have been possible. It is a malleable material. So, you can sort of make this operation. So, what will happen to the surface when finally I get the steel plate out to my desired thickness, right. Suppose this steel plate has come out like this. So, what I have on the surface? The surface material, the surface there will be oxidation taking place, because of that it was at a high temperature exposed to open atmosphere. So, thus there will be a oxide layer forming on the surface, right, and it is under pressure. So, in the process that that layer of oxide will be firmly bonded to the plate surface. That layer is referred to as meal scale, right. So, meal scale is nothing but essentially a combination of FeO and Fe2O3 and all that, right. So, it is nothing but meal scale is nothing but the layer, the oxide layer what forms during the fabrication of the plate, during the rolling of the plate in the steel plants, right. So, this forms, and now you know the steel plate has been formed, it lies there and then it is delivered to the shipyard. As and when you buy it, it will be brought in ship or railways or truck, whatever, and will be dumped in your yard, in your steel stock yard. So, the plate comes with this layer built in, this mill scale layer is there, and also it may absorb moisture in the process. Some H2O also goes in, there can be some hydrated oxides forming, all those things will happen. But what you will have is a steel plate having layer of mill scale. That is what it is. That means from that point we start. Now, why we talked so much about this mill scale? Because this mill scale temporarily, till such time it came to the yard, it actually gave protection to the steel surface. Means further corrosion or rusting, as we call it, further oxidation did not take place, right. It did protect. So, that way it has a positive role to play. Now, the next stage of operation in a shipbuilding operation is, well, you have the steel stock here, right. From there the material is supplied, it goes to a series, it goes to a kind of a rolling machine, and then enters a chamber where some operations are carried out, and then we get the so called finished prepared steel, or I can say processed steel, or well, prepared steel means ready for subsequent cutting and fabrication operations. That means at this stage, from here all the other operations start. Basically, all operations I am showing in one block, that is essentially cutting, shaping, welding, isn't it? And to this there are necessary inputs coming in as that of other in a very simple way. We can see all the activities. Here I have elaborated it, here I have clubbed everything. This is the actual fabrication work. In this zone, I am doing the actual steel fabrication. By steel fabrication is not steel making. This I was talking about steel making. By steel fabrication, we understand that the steel plates are there, ready to use. Ready to use means, well, what we do in fabrication, we have to cut them to the required size, we have to bend them to the required shape if required. For example, your ship's bow you want to fabricate, so there will be bent plates needed, right. Then what I will have to do, I will have to put them together, weld them, so you get the ship hull, and simultaneously do other works which I have referred to by this arrow, putting the engine in, fitting the air conditioner, the piping, pumps, machineries, everything, superstructure, and finally get the ship, right. So, before it comes here, so work starts with the steel material, because you start with the hull fabrication. So, for the hull, how the work goes? From the steel stockade, you take the plate, make it ready for these operations, cutting, shaping, welding operations. So, what is done here is something called plate preparation. That means you have to prepare the plate. For construction, plate preparation you will have to do, because you have got the raw steel plates from steel plant. You have to prepare them so that they become good for subsequent usage, and finally will be well for the product, good for the product. So, something called plate preparation. So, what we need to prepare there?
So, is welding not possible on the mill scale itself?
No, it is not whether it is possible or not. We will just come to that, why this preparation we are doing, right. Some preparation, because we have seen what we are getting the plate raw material as, we are getting it with some mill scale. I have not said one more thing, what in addition to mill scale we may have is the plate may remain distorted, means not absolutely flat, for the simple reason it has been handled many times in the steel plant. It has been lifted and loaded on trailer, transported, again lifted by crane, again unloaded, again lifted by some crane and loaded for further operations in the shipyard. So, the plate may have deformed, bent. So, before we start working on the plate, I need it flat, straight, because that is my datum. I know in a 2 dimension what I know the shape, I know the dimension. Then I cut it to the required size, and then I shape it, give it a 3D shape as per my hull form. So, I need it flat. So, that means preparation is needed. One is to straighten the plate, for straightening there might be some deformations. So, I need to straighten. Another aspect which is not visible, that needs to be removed, that is residual stress. In the very process of fabrication of the steel plate and also subsequent handling, as it can impart deformations, also it may impart residual stresses. It is very likely that the plate will have certain level of residual stress, and as you know, residual stress as such does not do any harm. Apparently, it does not do any harm, because at some part of the plate will be in tension, some other part will be equally in compression. So, it neutralizes. But if it remains, then what happens? Subsequent operation, the stress level may get changed, and it may lead to deformation of the plate, may lead to lessening of the fatigue life. So, all such things may happen. So, it is preferable to remove the residual stress. So, straightening is required, residual stress removal is required, and then I would say mill scale removal is also required. So, plate preparation will involve these 3 operations. Once these 3 operations are done, then the plate is ready for putting into this sequence of activities, cutting, shaping, welding, and finally to the final shape. So, this is what plate preparation, right. So, I have shown here this area in this when I pass the plate through these rollers, right, that is essentially straightening being done. Straightening as well as stress relieving and residual stress relieving. What happens is, what I am drawing here is a 5 roller machine. There is a set of, this is something different. Here only 2 rollers applying sufficient pressure to squeeze it down to the required thickness. Here 2 sets of rollers, also necessary force should be applied. These are all connected, right, such that they can be together, necessary force can be applied, such that when the plate comes, as it enters, this roller bends it down, the middle roller bends it up, and again it bends down, and ultimate result is it comes out flat, right. This middle roller is pushing it up, this one is pushing it down. So, essentially the plate is being subjected to a stress level much beyond the elastic limit. These deformations are large deformations, means the plate is physically getting substantially bent. In the process, in the cross section, the stress level, if this is your neutral axis, stress level would look somewhat like this. What does that mean? What I have tried to draw? That means this is my yield point stress. So, the almost the entire section has yielded. That means almost along the entire thickness, the top part was in tension, the bottom part in compression. In the next sequence, it just reverses. So, I have given here 3 reversal, stress reversal, right, in the process. So, what I am doing, this is being done at the room temperature, So, this is a kind of a cold work I am imparting to it. Stress level is exceeding the yield point stress in the plate. So, through a cold work with stress level exceeding yield point stress, your residual stress gets removed, because residual stress generally is of the order of yield point stress. So, I exceed that stress and I do it several times. In this case, I have done 5 times. I can do it, sorry, not 5 times, 3 times. I can do it 20 times, right, depending on my requirement. That means there are machines where you have several rollers, right, several rollers, and the same rolling operation, stress relieving and straightening operation is done. So, in this case, what will happen? It will go like this, I mean almost as if, anyway, several times. So, this is a 5 roller machine, this can be a 21 roller machine. What is the difference? Difference is that for thick plates, I can use less number of rolls. For thinner plates, I need to do it more number of times. That means, if I have a say 6 millimeter plate to be straightened and stress relieved, you may need to do this operation of bending it in this direction, again in the opposite direction several times more compared to a plate of say 20 millimeter thickness. A thicker plate requires straightening machine with less number of rollers, thinner plates require with more number of rollers. So, generally say up to 10 millimeter thick plates, a 21 roller machine is required, whereas for say 16 millimeter and above, a 5 roller machine will do, right. So, very first operation in the entire process, which is referred to as plate preparation, Under that plate preparation, we have under that sub activities are straightening and stress relieving, and then once that is done, it is directly fed to the this next activity. The next activity, that is mill scale removal, right. So, these are taken together in plate preparation. So, what we do in this mill scale removal? Here again, if I see, it is mill scale is removed, right. In the operation straightening and residual stress removal, they are being done simultaneously. The process is such that both the things are taken care of by one operation, passing it through those rollers, straightening machine. Once it comes out flat from that, then it immediately enters a next chamber wherein mill scale is removed, right. Now, what will happen if the mill scale is removed? What physically happens? No, physically what happens is you get a very bright steel surface. With the mill scale, the steel surface was dull, because that was the oxide, it has a dull color and it is already oxide. So, no more further oxidation, no more rusting. Rusting is nothing but oxidation. So, it remains as it is. Now, the moment I forcibly remove that scale, I get a very bright shining surface, really shining surface, that is the pure steel surface. But if I keep it like that, again it will rust immediately. So, I need to protect it. So, some kind of painting, which is referred to as priming. So, priming is done. Once priming is done, now all these operations can be automated. That means, as you can see here, these are fed through, say, roller conveyors. You put it on a roller conveyor, it rolls, the plate goes in, it is again all basically roller. So, it goes out. Again here you have the sort of transporter is a roller conveyor, it goes in, right. Inside also. So, it is a continuous automatic process. The plate is just moving from the steel stockade. With the help of a crane, you lifted the plate and put it on a material handling device. The device is roller conveyor. You have seen conveyor belts carrying coal or sand or ore. So, it can be just roller, like some of you, I mean, in airport you have may have seen where those things are taken, right. So, it is nothing but the rollers are powered. If it rolls, whatever is there on top will move. Simple, but it is a very effective means of material handling. So, the steel plate moves, goes through this straightening operation, straight away it goes out. Instead of dumping it, again it goes on a conveyor system, enters this chamber, mill scale. I have drawn 3 chambers purposely. So, in this the mill scale is removed, central chamber, it is primed. Since it is a continuous process, primed means what? A kind of a paint is being put, it should dry up. So, this is a drying chamber, simple, and it comes out ready plate, right, ready material. So, priming, drying, right. So, that is what is the entire operation of plate preparation: straightening, residual stress removal and mill scale removal. There are various methods of, we have seen how straightening and residual stress removal is done, it is simple. How mill scale is removed, we will talk about that, what are the various methods, but the question still remains, why do we remove it? What is the problem if it was there? Because I told it protects the plate. I need not do that priming and drying, it automatically is protecting. So, it is removed because, as I have said, that it has a, because of the very process of manufacturing, this oxide layer forms and the bonding of the oxide layer with the plate is very strong. It has a very strong bonding, but over period that bonding becomes weak. This is also very interesting phenomenon. Over period this bonding becomes weak. So, if the bonding becomes weak, what will happen? It will peel off. Just the plate is standing there and suddenly you will find that a small chunk falls off, the chunk of that oxide layer. Physically, if you keep the plate standing like this for good number of months, one day you will find lot of dirt has accumulated at the base of the plate. What has basically happened? That these chunks have fallen and got accumulated there. So, that is the problem. So, if we do not remove the mill scale and build the ship, eventually apart from problem of welding, in welding what may happen, the weld deposit may get contaminated with this oxide. So, before welding I have to scrape that surface thoroughly to remove any mill scale if it is there, right. So, welding is only one small problem. Bigger problem is that you build the entire hull or the entire structure, whatever you are building, and then, well, you will have to put it in service, and the service condition is that it is a rather a corrosive environment. So, one of the means of protection is painting, right. One of the most effective means of corrosion prevention is by providing a paint film, painting the surface. By painting the surface, what you basically do?
Avoid contact of oxygen.
We avoid the contact of the corrosive medium, right. In general, that is corrosive medium. That corrosive medium consists of oxygen, water, electrolyte and whatnot, right. In general, corrosive medium, that is one way of looking at it. Other way of looking at it is by painting. Essentially, I have made a film, made a barrier between the structure and the corrosive medium. I have insulated the structure, right, from the corrosive medium. Insulated against what? Well, against corrosion. How? Again, by insulating the corrosion current cannot flow, or in other words, just insulated it. So, it will be well protected if that insulation depend on the life of that insulating material, or depending on the will depend on the life of the paint film, how long it lasts. Now, if mill scale is not removed, then what will happen? After some time, the mill scale will get peeled off along with the paint film. So, your paint may be of the highest quality, the film, whatever it has formed because of the paint after drying or curing, that has the required thickness, required adhesion with the scale surface, but the whole scale gets peeled off. So, that is actually is the problem. So, your entire purpose of corrosion prevention through painting goes waste. You cannot, because it will get peeled off along with the paint film and is bound to get peeled off. Because that is the thing, with time automatically this bondage between the mill scale as well as the plates and the plate surface, it reduces, right. So, that is why what we should do is we remove it at the beginning and then give a suitable protection. That protection is that primer coat of paint which is applied, and when the construction is complete, final, then over that primer coat we provide additional layers of painting depending on the requirement, right, depending on the requirement. So, that paint coat will remain. How long it will remain? That will depend on the life of the paint film, the quality of the paint, not on the quality of the steel or any such thing. Previously, it was on the quality of the surface. So, the paint life depends on the quality of the surface. The surface has to be that, because your paint life is one of the important aspect. Why it is important? Because if the paint life is poor, then you will have more corrosion. If you have more corrosion, means your operating cost goes up, the ship owner's operating cost. Why? One of the aspect is the hull surface becomes rough, your resistance increases, powering your power requirement increases, fuel consumption increases. Second aspect is it's corroding, means you will have to dry dock the vessel, sort of clean the surface and then repaint it. All that costs money. If the corrosion is too much, maybe you will have to replace the plate, you will have to put in new plate, you will have to cut out that corroded part and put a fresh new plate. All these are very expensive. So, you lose money. Instead, if I have lose money means the paint you have applied, it was supposed to protect the ship hull for say 5 years. That means your calculations are like that. You know, for 5 years you have implemented this corrosion prevention mechanisms. So, for 5 years this will be the case. Now, if it is not properly done and that 5 year will be done, will remain properly protected, provided the paint film lasts that long. It will last that long provided the proper surface preparation has been done, otherwise the paint film life will be reduced. It may get reduced to 3 years, then again you lose, right. So, the paint life depends on the surface quality over which it is being laid, the paint is being applied, right. So, and there are other aspects also depending on humidity, temperature, thickness of layer, those are other aspects, but for the time being on the surface quality. So, what is that surface quality, how we achieve? That is what we achieve through plate preparation. The desired surface quality we achieve through plate preparation. What is the general thing we get? That after the surface is cleaned or the surface is cleaned of the mill scale, I told that we get a shining surface. That shining surface gives us a quality of, there is how you are removing it, by which method and how effectively, how all that, it leads to different quality of the surface. That quality is not only that how effectively the scale has been removed, that is one, other is how smooth is the surface, right. So, those are referred to as by some standard which is say SA 2.5, this refers to, this standard, this refers to there will be a surface smoothness is to the standard of SA 2.5. This SA scale goes from I believe 1 to 5, it is somewhere in between. As you go higher, it becomes more and more smooth, but we need somewhere in between. SA 2.5 is a good quality of surface finish, right. So, that is how we see that the mill scale should be removed before you get into the actual fabrication operation. Main reason for removing is that if you do not do that, then immediate problem would be the welding, means welding you will be able to do, but there would be a possibility of more welding defects coming in the picture because of inclusion of these oxides. There will be sort of the weld deposit will be contaminated with the oxides if they are not removed, but that is not a serious problem because I can simultaneously remove it before the welding. Long term problem is the mill scale will peel off and it will be subjected to corrosion, heavy corrosion. So, that is the main problem. So, mill scale should be removed. So, that is what that is done through that process of what you call plate preparation. In the, it comes within that thing of plate preparation, it should be removed. Then that whole operation is done, can be done in one go. You remove the scale, prime it, dry it. So, next comes that how do we actually remove it? What are the methods, right? what are the methods? Tell me some of the methods. From common sense, you can guess one method at least.
We can hammer and
no, through hammering it will not go. The bonding is quite strong.
use of solvents.
Yeah, one method could be use of solvents. We'll give a good name to it. What is the first and foremost method could be?
Scraping it off.
Scraping is also not easy because I said the bonding is really strong. It's not easy. First and foremost method could be natural descaling, natural process, because I told with time it peels off. So, I just stack the plates vertically, I just keep them. In a natural process it will peel off. So, first and foremost method can be referred to as a natural process, natural method. In the natural method, what is done? Just imagine a situation like this. Say this is my ground level, some pillar is there and I have just stacked the steel plates like this in between, say some wooden blocks, and say these are my steel plates which are separated by wooden blocks, so that they are not touching each other. It can be, isn't it? You just keep them standing, means basically they are the plates like this standing. Okay, these are the. So, in the process what happens? That means you stack them in the stockyard and let them lie there in the open. So, it will be subjected to your rain, your heat, your cold, everything. In the daytime it will get heated up, in the night it will cool down. If it rains it will be washed with the rain waters. So, that natural process, as I said, automatically it gets loosened and it will peel off. So, keep it like 6 months, after 6 months you take it, plates will be fairly cleaned in the sense mill scale has got removed. So, that could be one process, very crude process, but one process. The basic drawback what you wanted to say is,
Is it uniform?
yeah, basic drawbacks would be it will not be uniform, non-uniform. So, you cannot guarantee that 100% has got removed. There will be local rusting taking place, local corrosion, because in some places it will get removed early, some other places later, and the worst is some places it is bare steel, just vicinity it is mill scale. So, it will form a galvanic cell and the galvanic corrosion will set in. So, the place which is scale has peeled off, heavy corrosion will be there. So, after 6 months if you use really the steel, or after 1 year even, you still will have lot of patches. Some will be very clean, which has got recently the scale has peeled off, and the first, because this bonding is not uniform, some may get peel off say after 2 months, after 3 months and so on and so forth. So, the plate surface will not be smooth at all. So, this is definitely not a good method, but this could be one method, right. So, that is what is the natural process. I mean, one method in the sense, those who cannot afford other method, for him at least this is a method. That is how. Though this is again it has other drawbacks. That means you have to keep the plates lying like that for a substantial period of time. That means you have to invest on the plates, you have to buy the steel plate, keep it unutilized. So, that is also not a good business practice. That means you buy thing and it remains idle. though it is not truly idle, it is doing some operation, but that operation is not very effective. So, that is the natural process. The other processes are flame treatment, mechanical means, shot blasting, and that chemical you are telling some solvent, acid pickling. So, these are the, one can say, 5 different avenues you have to remove the mill scales. We will talk about them in the next class, how they are done, and we will see their effectiveness, which one is what.